The next topic is selective precipitation. The selective precipitation is when you have a solution and mix the ions. And if we add one reagent, we call it precipitating agent. It may form precipitate with all the ions, or at least part of the more than one ions. Okay. If it can form precipitate with more than one ions, then there's the issue of if we can separate the ions one after another instead of all precipitate. Because if you precipitate everything, that means there need to be more work done later to isolate the compound. The selective precipitation is very useful in industry. So for example, a couple of years ago, Samsung, it has a lithium battery problem. The lithium battery in the phone will catch fire during charging or even doing nothing. Become very extremely dangerous. So Samsung has to recall all the 12 million, I remember it's about 12 million new phones. And so what happened to the new phones? What will happen? The phone, it has many electronic parts, and there are many precious metals in the electronic components. For example, gold and silver, they're actually used in our actual cell phone, even though the amount is extremely small. But when you have 12 million phones and recycle all the metals in the 12 million phones, the metal can be quite valuable. So how to separate the gold and silver, copper, aluminum, there's some other precious metals. We use a selective precipitation. So the very first step, we separate the least reactive metals like gold. And then the following, the remaining is still a mixture of different metals. We use a selective precipitation. First, to make the silver precipitate, and the next step we precipitate is the copper, and the other others, just for example, how they separate. So selective precipitation is basically we add a precipitating ion or precipitating agent, is a reactant. Once we add in, there's a chance this ion will react, will combine with ions in the mixture. And the quotient, by the way, the quotient is calculated based on the ion that are in the mixture times the concentration of precipitating ions. In the beginning, there are no precipitating ions, so it's concentration 0. QSP equals 0 at the beginning. But as you add in more precipitating agent, the QSP will start increasing. From 0 becomes some bigger number. But as long as QSP is less than KSP, there will be no precipitate. Once QSP is larger than the KSP, then they will form precipitate. So when you have a mixture of different compounds, and the QSP for each potential precipitate will increase, start from 0. Well, only the precipitate will form only when the first QSP larger than the KSP. Then they will have a first precipitate. Keep adding more precipitating ion, it will complete precipitate the least soluble compound. And the other ions will mostly stay in the solution. But once the concentration precipitating ion increase to even higher level, and the first ion has already been separated, then there is a chance the second ion start being precipitated. And that's what we call the selective precipitation. So how do we know which ion form first? Basically, we calculate QSP based on the concentration of ions and also the concentration of the precipitating ions, the one that cause precipitate. And if you find out the QSP larger than the smallest KSP, then that will precipitate first. And so the selective precipitation is basically, we need to make sure the QSP is larger than the smallest, but it has to be below the KSP of the more soluble compound. And so we basically find out the range. What is the concentration of ion needed to precipitate each ion? Then start from the lowest requirement. That ion should precipitate first. And so let's see an example how we use that. So that's a general guideline. Basically, the QSP for different compound, we can calculate each. And only the selective precipitation is KSP of the less soluble. KSP for less soluble precipitate typically is a smaller KSP value. As we can see, the lower value for KSP means the less solubility. So when you have that, this will be precipitate first. Okay, the right hand should precipitate first. But we should avoid the other one. The other ions also from precipitate. So that means QSP, it has to be not be too big. It has to be no more than the more soluble compound KSP. And this guidelines, it may not sound like really easy to use, but as you can see an example, we basically compare the concentration of ions, precipitating ions, which give you the lowest. That means that compound should precipitate first. Okay. The lowest KSP typically should precipitate first. And so the maximum concentration of precipitating ion, we use KSP of the more soluble to calculate. The KP of the more soluble means higher solubility, and that should require, since it's more soluble, it requires higher concentration of the precipitating to form precipitate, because it's more soluble. The least soluble, it needs the least amount of a precipitating ion to precipitate. Okay. And so let's see an example of how we apply this. Sounds like not the easiest to understand, but once you see the real example. So this example has the, we have two ions, metal ions, that potentially can form precipitate. And so you can see the first solution is magnesium chloride, the molar is such. And also we have a copper chloride. As we learned about the solubility rule, most metal form insoluble metal hydroxide. So hydroxide is a very common precipitating ion because it can potentially combine with metal, form precipitated with most metals except the alkali metal or ammonium. But hydroxide is very common. There are some other precipitating ions are the sulfide and carbonate and phosphate and so forth, just name a few. So here we talk about what kind of hydroxide concentration can separate these two metals, which means form precipitate with one of the metal ions and keep the other ion in the solution. Okay, so we have the KSP for both, KSP. And we have the metal concentration. So to form precipitate is when the QSP is larger than that is form precipitate. It'll form precipitate. And now we have the KSP for both. We just need to find a concentration of hydroxide to make those ions precipitate. The QSP for each metal hydroxide, we calculate So let's say I do the magnesium first. Magnesium chloride, magnesium hydroxide. So I will calculate the QSP for magnesium hydroxide. To find a QSP for magnesium hydroxide, we need the magnesium concentration times hydroxide. 1 mole of magnesium have 2 moles of hydroxide. So the coefficient 2 will become exponent. Okay. So that's QSP should looks like. And the magnesium concentration is the same as the solution concentration, as 1 mole of magnesium hydroxide, magnesium chloride, given 1 mole of magnesium ion. That's what a QSP for magnesium should look like. To have magnesium hydroxide form precipitate, this need to be larger than KSP of the magnesium hydroxide, which is 6.3. Right, so that's the QSP for magnesium hydroxide to form precipitate. So we just need to find the concentration of the hydroxide to satisfy this inequality. And just divide by 0.2 from both and solve hydroxide.
Professor, just a quick question.
Yes.
Should it be 2 times the concentration of hydroxide on the inside of that exponent 2? Or 4, would it be?
Remember, this is not the ionic compound dissolving pure water.
Oh, okay.
Yeah, this is actually a solution that already have magnesium, a fairly high amount. Yeah, so don't use that. This is hydroxide, actually we need to find out. But this 2 come from the substrate. Because 1 mole of magnesium hydroxide have 2 moles of hydroxide. That's the V to 2.
Okay.
Yeah. So basically the rest is just try to solve this inequality, and it's very straightforward. 6.2 times 10 to the negative 10 divided by 0.2. And so finally, you solve the hydroxide. The answer, what I get is 5 points, round to 2 safe phase. So yeah, 5.6. And we add unit molar. So that's the QSP for magnesium hydroxide. And what is the hydroxide concentration needed to form precipitate with magnesium hydroxide? The copper hydroxide, copper-2 hydroxide, the similar is calculation is very similar. I will pause the lecture. I will let you guys find. Yeah, so that should be the answer key for that.
Are you supposed to flip the inequality sign when you divide by the molarity? Because like for the first example, it says that the concentration of hydroxide has to be greater.
Yes. But
the answer shows that it has to be less.
Oh, that answer key, not yet. We haven't got there yet. But this is only the, what we're doing here, it is for magnesium to precipitate. We should have that. Magnesium to precipitate, we should have that. Okay, that's the first part. And then for the copper to precipitate. Copper to precipitate, we calculate the exact same way. And we use copper and hydroxide. And we use a copper concentration 0.10 and times hydroxide. Larger than the copper is 2.2 times 10 to the negative 20. All right. So anyway, we skip the solving because it's pretty obvious, just like we did it before. The hydroxide has to be larger than 4.7 times 10 to the negative 10. Yeah. So whenever you solve something, we have to give a meaning. This we did this hydroxide larger than this. It is the condition, the condition of hydroxide for copper to form precipitate. So for copper to precipitate, we need a concentration of hydroxide that is this. And so for magnesium, concentration has to be that. For copper is this. How to separate? When we increase the hydroxide concentration, when we increase hydroxide concentration, which actually means increase pH, increase pH. If you start from a low pH, low hydroxide concentration to high concentration, we'll reach this point first. Okay. When you increase the hydroxide, it will hit this mark first. So as the hydroxide concentration increase, we need to think about which ions, magnesium or copper, which precipitate first. When we increase hydroxide, which precipitate first based on our calculations? Increase means start from, let's say 0. Okay, actually there's no 0. But let's say pretend we start from 0 hydroxide and increase to a small number. And we can see it will hit this mark first. So as we increase hydroxide, the copper will precipitate first. Because for magnesium to precipitate, the hydroxide need to have a higher level. Actually, it's much higher level. 5.6 10 to negative fifth molarity. So adding hydroxide, increased concentration of hydroxide to the solution. Copper will form precipitate first. And then even higher hydroxide, magnesium will start precipitate later. And so to separate the metal ions, that means we precipitate only one of the two ions first. And as you can see, the hydroxide increase copper first. So basically, we need to decide what hydroxide concentration. Only copper precipitate, whereas the magnesium did not precipitate. Since copper precipitated first, as you can see. This will precipitate first, and so that means to separate, well, let's keep the only copper form precipitate. Magnesium do not precipitate. That would be the ideal concentration. Does this make sense? Selective precipitation means we precipitate only one ion first, and that ion typically is less soluble, which means the low KSP value. And between these two, between magnesium hydroxide and copper 2 hydroxide, the copper 2 hydroxide is less soluble. So that should form precipitate first. And that's why the answer is we need to keep the copper, since copper precipitated first, let's make the copper precipitate. And that required the hydroxide has been than this concentration. Because as we calculated, when the hydroxide get to this level, copper precipitate. But since we're separating these two, separate, that means the hydroxide cannot be too high to make the, we need to keep the magnesium not precipitate. So that way the separation can be achieved. And to keep magnesium not from precipitate, that means hydroxide, it has to be less than the precipitating concentration, which is, we calculate 5.6 10 to the negative 5. Rigorously, we can make it equal. Equal, that means solution just form saturated. It reaches equilibrium. When the hydroxide equals 5.6 10 to the negative 5, the solution just saturated. It's ready to precipitate, but not yet. It is because it form a equilibrium between the solid and the ions. So that's the consideration for the selective precipitation. The actual finding the range is basically, we calculate the concentration of the precipitating ion required for each ions. Okay. So that's why we calculate the hydroxide for magnesium first, okay, one by one. What is the concentration of hydroxide needed to precipitate magnesium? And also, because we have KSP for copper 2 hydroxide, we do the copper 2 hydroxide the same. Let's find out what is hydroxide needed to precipitate copper 2 ions. And then between these two, whichever is smaller, that should be the precipitate first. You can see between the magnesium and copper, this number is much smaller than the magnesium, which means copper should precipitate first. If your hydroxide, the precipitating agent, the precipitating ion, will keep adding, start from 0, and you keep increasing the quantity, the concentration. There will be the first precipitate. Whichever needs the less precipitating agent, it should be the first one to precipitate. And so the selective precipitation, it is basically use the KSP to find the concentration for precipitating ions. Precipitating ions always added later. We can always start from 0. 0 precipitating ion in the beginning. As we keep adding more, then there'll be more and more concentration, the more and more concentrated precipitating ion. And then the quotient will increase correspondingly. Because the quotient, it is affected by the concentration of the precipitating ions. And so the selective precipitation, we don't have much question about really ask about what range for which, how to separate. But we do have a question asked about the what concentration of the precipitating ion to precipitate. Okay, like the first part, the both calculations of the concentration of ions. We do ask this. The conclusion, which agent we add in, how to separate these two, that is secondary. The most important, we need to know how to find the concentration precipitating ion to cause precipitate. Basically, QSP larger than KSP, there will be precipitate. And KSP is constant. QSP depends on the precipitating agent. And so to find the concentration precipitating agent, this is how we find it. It's mathematically fairly straightforward. But combine these two together needs some thinking. The bottom line is concentration precipitating ion, the agent, it starts from low to high. And that's exactly happening in the industry. The industry, when we separate the copper with the silver, for example, copper and silver, we use precipitating agent. The KSP for silver chloride is very low. As we remember, the silver chloride is insoluble. So the KSP for silver chloride is very small. And the KSP for copper 2 chloride, which is very large, is because copper 2 chloride is soluble. That means by adding the chloride, copper should not form precipitate. And just because the threshold to precipitate copper is very large, it will precipitate the silver first as we add in the chloride, precipitate silver first. And then when you add to extremely high level of chloride, copper will form precipitate. But that's not very practical. So the selective precipitation is basically find out each precipitate, what is the concentration of the precipitating ions, which one required less. The one asked for less, it should be the one formed precipitated first. Because that's the least, less soluble among all the potential precipitate. Finally, which one use less precipitating agent, and that should be the first one precipitate. Okay, any questions on this? We saw both. Whichever the hydroxide is less concentrated, that means easier precipitate. As we add in more hydroxide, it'll be the first one to precipitate. In our quiz or test, we don't really have the ask about the decided which one, what is the range for these two. But it is the range, if asked, it should be the between. The range, it is between. In between the two precipitating agent concentration. It has to be larger than the smallest, but smaller than the more soluble compound. Okay, when the precipitating concentration is less than the upper limit, the second metal will not form precipitate. But when the hydroxide larger than the smallest, the first one, it will precipitate. Here, the copper will precipitate first. Copper precipitate first. And so selective precipitation is always more challenging to really fully understand. And there's a way to graphically, I have not really worked out a good graphic, but this is the, mine looks like. This is mine looks like. So let's say we have two reagents, two metal ions, and one precipitating agent. And this is the precipitating agent concentration. Precipitating ion concentration as X. The Y will be the quotient. But as you can see, there may be more than one ions, and then the quotient for both. Okay, let's say we have two compound, and their formula maybe have a different mole ratio, but nevertheless, the quotient for the possible potential precipitate as a Y. And so as the ion concentration increase, the quotient should increase. So it looks like this. It's not actually not linear, but let's just pretend they're linear. Precipitate ion will form the, this is a quotient 1, the first ion, Q1 increase like this. The Q2 will be different compound. Different compound, because different formula and different concentration of ions, you have a different curve. Let's pretend also linear increase. This will be quotient 2. As you increase the precipitate ion concentration, both quotient will increase, start from 0. At a point 0, the concentration 0, there's no precipitate. The quotient equals 0, much, much smaller than the KSP. And then we have these two, we have 2 KSPs. The first compound, you have a KSP1. Oh, this one, sorry, I'll make it 2. The second compound, let's use the blue, and the first compound, use the red. The compound 1 has also a KSP1. KSP1's here. So what is the concentration for Q1 to form precipitate? For the compound 1 to form precipitate, the quotient has to be larger than KSP1. So this is the range from here. Compound 1 precipitate. Let's say we named as a precipitate 1. And precipitate 2, the second compound, have different colors. Okay. The second compound, Q2, KSP2. For the compound 2 to form precipitate is where the quotient Q2 larger than KSP2. This is the second compound form precipitate. So basically, the minimal concentration for compound 2 to form precipitate, this is the minimal concentration, as in the X. This is the concentration of the ion for first compound to form precipitate. So what is selective precipitation is here. This part, if your concentration of ions, precipitating ions, is right here, then you have only compound 2 form precipitate, whereas compound 1 will not form precipitate. So discuss selective precipitation. A simplified picture, I can draw a graph. I use the concentration of precipitating ion as X. As we keep adding more and more precipitating ion, the precipitate should form one by one. How they form? You compare Q and K. So that's the more visual. It's kind of oversimplified, but the more visual way to understand what is selective precipitation. Selective precipitation is in this area. You achieve selective precipitation, keep your concentration in between. So that'll make the less soluble form precipitate, but the more soluble will not form precipitate. Okay, so that's about a selective precipitation. The actual graph, I draw the 2 straight lines, and the slope is constant. The actual, because the quotient, it is oftentimes square or cube of the concentration. That actually is not a straight line; it's a curve, but the concept is the same. The last part of the chapter, is almost the last part of the chapter, is the common ion effect on the solubility. This is actually the one example of the Le Chatelier's principle. So this first picture shows you the solution. You have a lead-2 chromate. Lead-2 chromate, it has very low solubility. So once mixed with water, it thoroughly mixed, you have this part is almost clear. It's basically a clear solution. And the solution saturated because you can see once the dissolving process stopped, you have a significant amount of precipitate still not dissolved. So whatever here, the supernatant, the upper clear solution, it is a saturated solution. Okay, and then we do something. We add the sodium chromate solution to the top. By adding the sodium chromate, this equilibrium, now we have an increased amount of product, the right hand, the product. It will shift the equilibrium to the left, which means it will form the solid lead-2 chromate. That's what you see the yellow precipitate formed here. It is basically the application of the Le Chatelier's principle. Another way to look at this, it is the lead-2 and chromate, both are precipitating agent. If you keep increasing the amount of precipitating agent, it will facilitate precipitation, form precipitation. Form precipitate, that also means the solubility of the lead-2 chromate actually decrease because the extra common ion, the product ion. So that's what we call the common ion effect on the solubility equilibrium. Very similar to this is the buffer effect. You start from the weak acid, and then you add salt of the weak acid. Adding those salt, weak acid, it shifts the equilibrium to the left. It prevents the dissociation of the acid, becoming the hydronium ions. And the calculation on the common ion effect. This is the earlier practice. We did this. I hope I recorded yet. Okay. We calculate this calcium hydroxide solubility in pure water is 0.012. And this is the calcium hydroxide solubility in pure water, okay, in pure water, which means there are no calcium ions or significant hydroxide ions in the water to begin with. Now we have a situation, the calcium hydroxide, what if the calcium hydroxide, it is put into a potassium hydroxide solution? What will be the solubility? Keep in mind the potassium hydroxide is a soluble ionic compound, completely dissociated into potassium ion and hydroxide. So in the solution, there is significant hydroxide concentration. And as hydroxide being part of the ions in the solute calcium hydroxide, this extra high concentration hydroxide, it should reduce, inhibit dissolving of the calcium hydroxide. And here's we show you how to do the actual calculation. What is the actual solubility under this circumstance? To solve that, we use ice table. So as we use ice table, we have the calcium hydroxide. It dissolves into calcium ion and hydroxide ion. Oftentimes the state, I don't really put in there, just kind of reduce the workload. Ice. So same, we put S as a solubility. This is the part to be dissolved. So that means in the end it becomes 0 and change the negative X. So that's about the solid state solute. Okay. In the beginning, the calcium concentration, as you can see, there's no calcium mentioned. That means in the beginning, before dissolve, there should be 0 calcium in the solution. And then we look at the hydroxide. Hydroxide before the calcium hydroxide dissolve, there's a 0.10 molar potassium hydroxide. So the hydroxide is not 0. Okay, what exactly the concentration of hydroxide? This compound, 1 mole will dissociate, give you 1 mole hydroxide ion. So the molarity hydroxide equals molarity the potassium hydroxide, which equals 0.10. So you can see the hydroxide before the dissolving taking place, it has a very high concentration, 0.10 M. So let's put that down here. This is the ion before calcium hydroxide dissolve. What there's the amount is already in the system. And then to calculate the ice table. So basically, we're going to use the ice table and combine with the KSP given to solve for the S, just like we did it before, but with a slight difference because the hydroxide, one of the 2 product ions, the initial amount is not 0. Okay, it's not 0. So we have the calcium hydroxide dissolved. This part should dissolve and make it 0 in the end. And the calcium should be positive S. How much is the hydroxide change? Okay, what is change in the hydroxide? Anyone can tell me?
S.
Yeah, plus 2S. Yes. Plus 2S. And then we find that over the end. This is S, this is 0.10 plus 2S. That's the end. And then we can set up the equation. This is the solution reaches saturation. When the solution reaches saturation, become equilibrium. And that means the KSP should equals QSP should equals the ion product expression calculated. Okay. The KSP should equals the calcium concentration, which is S, times the hydroxide. Hydroxide is 0.10 plus 2S. The hydroxide coefficient 2, that becomes power. The QSP should equal that, and the QSP has a value which is 6.5, 10 to the negative 6. Okay, so the next step, we should distribute and then finally set up an equation and then finally solve it. But unfortunately, this equation, I don't think we have learned enough to solve that. And we have to assume, we have to use approximation. So look at the number, how can do the approximation? With this S, okay, by the way, this section, it should be at least 0.10. Okay, this section should be larger than 0.1. And you have a square of 0.1. That's fairly big compared with this number. So that means this S must be very small. Okay. This S must be very small because this portion is more than 0.01. And these two multiply should give you a small number. that S must be very small. This S must be very small compared with 0.10. And that means I can use approximation. So whatever here, and this, since S is much smaller than, we assume much smaller than 0.10, that S becomes negligible. So that means it simply gives me this. As we use approximation.
Professor, I have a question.
Yes.
Why can we use the approximation to show, say that 2S is negligible, but the first S on the outside isn't, even though they're the same value?
Okay, the explanation, the S, you cannot make the first S become 0, by the way. If make first S become 0, then this
Yeah, then it doesn't work out.
Yeah, you sound undefined. Your S will be undefined.
Mm-hmm.
And the second one, remember, we can always assume the small and later do the validation.
Mm-hmm.
And this is kind of, if those of you did some the pre-calc or the calc 1, you probably learn something similar when you do the derivative, what do you call it? First derivative, how you solve the first derivative. You basically, there's some part you cannot neglect, but there's part when you have a bigger one, like the S compared to 0.1 is negligible. You can always assume that and then solve, and then later get back to validate. This is a mathematical treatment. Unfortunately, I'm not a mathematician to explain this, but this is how it should work out. And if you want more explanation, it's kind of like this. Let's say the, this is not quite necessary, but this is, let's redo that. S times 0.1 plus. Okay, so this portion will be larger than 0.1 squared. Agreed? Does everyone agree?
Yes.
That should be larger. And so let's say I divide by 0.1 squared on both. It's not exact. Keep in mind, this is slightly bigger than that. If you divide by the, I should get, I divide by 0.1 squared on both. Okay, no matter what it is, I just kind of divided by something. This is solving is kind of very crazy. It's not really what we learned before. Since you are divided by this on both, let me kind of do more algebraic. It's not, my writing style is have a big lag. I hate it. I hate the lag. Yeah, I think this is probably work out better. All right. This is simple. It's very straightforward. No approximation, correct? All right. S equals that. And this portion is larger than 0.02. So, oh no. I can actually prove it. Do you agree with that? Even though I don't know what the S is, but actually I can mathematically prove the S should be smaller than that number. Because the denominator more than 0.01. Denominator more than 0.01. So that I end up like this. Make sense?
Yes.
And so, and you can see the S is so small compared to 0.1, you simply just round them off. Just make no difference in the final value if you keep two sig figs. So I think it justifies. Yeah, we use approximation to solve this problem. If you check the book, I don't think the most book they bother explain use approximation. They simply just use the KSP divided by this divided by the common ion concentration raised to the power or whatever, and just find a final solubility. But the actual work is we should use ice table and use approximation. Use approximation.
Okay, thank you.
Yeah, no problem. So that's where the approximation kind of applies. Since the 2s is compares with 0.10 too small, that use approximation just becomes this. And then we solve the S. The S is approximated, of course. It is KSP, which is this, divided by 0.10 squared. So that'll give me 6.5, 10 to the -4. That is the approximate solubility. And don't forget units. Solubility has a molar, capital M, as a unit. So keep in mind the S, what do we find and solve? It is molar solubility. But this is the new molar solubility, is when there's a common ion. The compound dissociate, produce ions. The solution already have high concentration of this ion. And you can see the results. This solubility is much, much smaller than the impure water. .012 M. It is solubility in pure water. So why is there a difference? Why the in the potassium hydroxide solution dissolve much less? It is because potassium hydroxide, it has give you high concentration of the hydroxide. It shifts the equilibrium back to the precipitate, which means also means less dissolving. The calcium dissolve in the solutions only, the calcium concentration only is such a number, very smaller than the impure water. So the concentration solubility of an ionic compound will become much less if the solution has high concentration of the common ion. And here's how we calculate. Use ice table and use approximation. Use approximation. So the approximation comes from here. That becomes this. So that's the common ion affect the solubility equilibrium. Any questions? Ice table and also the initial concentration is not zero. There'll be many homework questions similar, many of them simpler than this, because in many questions the ion ratio is 1-to-1 ratio. Then the change is much less. But it's basically the same principle. Use approximation. And we're getting to the last part of the lecture. The solubility of the ionic compound can be affected by the pH. And that's because dissolving of the ionic compound oftentimes, so for example, calcium carbonate. Calcium carbonate is made of calcium ion and carbonate. Carbonate is conjugate base of a very weak acid. So that means this ion have very strong tendency to combine with the proton. And once combined with the proton, this concentration will decrease. Decrease. The concentration decrease in the product end will help shift the equilibrium to the right, which means it will increase solubility of the calcium carbonate. Another way to look at this, because the carbonate it is involved in two competing equilibriums. The first one is with calcium. The other one is with hydronium, with acid. And so if you increase the one of the competing equilibrium, that will help drive down the concentration of the carbonate, and that'll cause the more dissolving. So that's the pH can affect equilibrium, and you can see there are many cases. As we learned about the solubility rule in the first semester general chemistry, we learned about there are many compounds are low solubility. So for example, the carbonate, phosphate, and sulfide, and sulfite. All these ions, when they combine with the metal, form insoluble, which means a low KSP ionic compound. So when those compounds dissolve in water and dissociate, produce those ions, each of those ions are the conjugate base of a weak acid, so which means they are fairly strong base. Changing pH, adding acid will help driven down the concentration because the proton react with those, and that in turn will make the compound more soluble. Solubility can change with pH. And that's what happened with the calcium carbonate. For example, marble. The marble in nature, it is a reformed calcium carbonate compound. And when you put a marble into the acid, it'll dissolve, produce carbon dioxide. And that is because the acid combined with the carbonate that comes from the dissociation and drive down the concentration and facilitate dissolving. And so the effect from the changing pH, adding acid, it'll affect the solubility of many compounds. And so here's a little short practice. The the first one. Lead bromide, copper 2 hydroxide, iron 2 phosphate. How the adding hydronium, which is the acid, will affect the solubility. The first one, lead 2 bromide. This dissolving give you bromide. The bromide is conjugate base of a strong acid. So this is very, very weak base, which means weak base don't react with hydronium. It will be no reaction. Hydronium will not react with the bromide. So that means adding hydronium have no effect because The bromide ion comes from dissolving. It is an extremely weak conjugate base of a strong acid. As we know, the HBr is a strong acid. So since the base is so weak, and it won't react with the acid. It's a very weak base, actually. It's a very weak base because it comes from a very strong acid, HBr, hydrobromic acid. The second one, copper-2 hydroxide. Copper-2 hydroxide. The hydroxide is the conjugate base of, can anyone tell me the hydroxide is a conjugate base of what acid? What's the conjugate acid of hydroxide?
Water.
It's water, yes. So basically, you add a proton to the base, become conjugate acid. Water is a very, very weak acid. We consider neutral, actually. So that means hydroxide is a very strong base. Very strong base. So I should add a very, very strong base. So that means it will react with proton to a very high degree. That means adding hydrogen, it will react. And once it reacts, this concentration will decrease. And according to Le Chatelier's principle, this equilibrium will shift to right, which means it will dissolve. It will have effect. And it will affect. And to be exactly, the effect is increase the solubility. Solubility will increase. Okay, so this chapter, we have the molar solubility in pure water, and then molar solubility with a common ion effect. And then we have Q and K. Each one is different, so make sure pay attention to the difference. The molar solubility in pure water is when there's no ions that interferes with dissolving, just water. And you use the, we have 4 equations to calculate. 4 equations, depends on what the ratio between ions. The molar solubility and KSP have 4 equations to relate. And then we have a common ion effect, use ice table, and use approximation to solve. The common ion reduce the solubility. And here we can see the solubility can change when you add a reagent to remove the ions, because of reaction. So basically, if the dissolving produces a fairly strong base, the solubility will be affected by the pH because of reaction. The reaction will cause the reduction, the losing of the product ions, keep the equilibrium shift right. Okay, so that depends on if the dissociated ion is a strong base or weak base. Okay, the last one, iron 2 phosphate, iron 2 phosphate. The phosphate is 3 minus, and iron 2 is 2 plus. So that's how we should balance this equation. And this dissolve will give you 3 irons and 2 phosphate. Okay, so this iron don't react with acid because it's positive charge. It don't react with positive charge hydronium. But this one, this is come from a very weak acid, the hydrogen phosphate. So this is fairly strong base. It's also very strong, very strong base, because the conjugate acid, which is this, is very weak acid. Keep in mind, phosphoric acid is already a weak acid. And with phosphoric acid, keep two more protons, that becomes even weaker. When the weak acid comes, the conjugate base is very strong base. Since strong base, hydronium will react, and so this, it will affect solubility will increase when you add the hydronium. So that's how you predict if the adding acid or changing pH affect the solubility of the compound. And this material will not be significantly involved in the future tests or quiz, but for knowledge we should know. So basically dissolve, see if the ions come from the strong acid or weak acid. If the ion come from strong acid, which means weak base, then don't react with hydronium. Only strong base react with hydronium. And then in the end, the results is the solubility will change. Equilibrium will shift to right because the losing the product ions. The reaction reduce those anions concentration. And the reduce in the product concentration shifted the equilibrium to the right, cause more dissolving. In nature, this is actually involved in many landscape evolution over the long term of history. The most significant is limestone, because limestone, it dissociates, give you carbonate, which is fairly strong base, carbonate ion. That means the change in pH can affect solubility. And in nature, the carbon dioxide being part of the natural cycle, the photosynthesis and the metabolism cycle involve carbon dioxide. And also the underground Earth's volcanic activity produce carbon dioxide. All these affect the pH. And so you can imagine the pH change, it will affect the landscape that is made of limestones. So basically, when there are high level of carbon dioxide, it'll eventually produce more acid, and that will make the limestone dissolve more when there's more carbon dioxide. And then the heat will help dissociate and produce calcium carbonate deposit. And so that's in nature. You can see those, the stalactite and stalagmite. A stalactite is the one that hangs from the ceiling. And those of you who've been to the crystal cave or those underground caves, you see there are some locations have this kind of structure hanging down toward the ground. That is the stalactite. And the stalagmite is right under, is where the stalactite is formed. It grows some stalagmite. So what happened is the calcium carbonate being dissolved elsewhere, and once it goes into this location, it decomposes and forms calcium carbonate. And over time, those dissolve, even the dissolve, and once dripping down, it also can decompose, give you calcium carbonate, the solid. But keep in mind, in nature, this keep changing as the solution become, the running water or the groundwater become more acidic or less acidic. It'll change its shape over time. It is the equilibrium between the dissolving of the calcium carbonate and the pH change caused by the CO2. About 50 years, 70 years ago, in the past 100 years, the acid rain became a serious problem because the burning the coal to produce electricity, and also the iron mill, iron production industry. When you burn the carbon, burn the coal, and also the minerals of the iron, they all have a high amount of sulfur. So combustion involving sulfur, it will form eventually the sulfur dioxide and eventually sulfuric acid. And that seriously reduces the pH of the atmosphere or the rainfall, so-called acid rain. And those acid rain can really affect the marble and the limestone, those landscapes. There are many marble statues have been corroded by the acid rain. It's just because the lower pH from the polluted rainwater, it basically facilitated dissolving, the dissociation of the calcium carbonate in the statue. And so the last part of, there's a little more on the solubility. A little side note, I don't think I have that in the PowerPoint.